Hello teacher, my name is Lider Bektaş and for our Computer Networks course, today I will be presenting a report summary on intelligent and connected vehicles. This presentation is based on the comprehensive research paper by Yang, published in Science China Technological Science. The main purpose of this presentation is to explore the current technological status, autonomous vehicles, and discuss the critical gap that still exists between industrial hardware and academic software. Here is our agenda for today. We will start with the evolution of mobility and classification standards. Then we will dive deep into the technical aspects, specifically the EE architecture, communication networks like CAN and Ethernet, sensors, and actuators. Finally, we will look at the decision algorithms and conclude the future perspective. Let's begin with the evolution of mobility. Historically, the automotive industry focused on speed and later on safety and efficiency. But the 21st century, the focus has shifted entirely to intelligence and connectivity. However, there is a core challenge we must address. The research identifies a significant gap. Industry giants are focusing heavily on building robust hardware platforms while academic researchers are focusing the theoretical algorithms. To achieve mass production, those two worlds must integrate. To understand autonomy, we use the SAE standards, which define 6 levels. Level 0 is no automation at all. Level 1 and 2 offer driver assistance, like adaptive cruise control, but the driver is still responsible. Level 3 is conditional automation, where the car drives itself in specific conditions. But the real goal is level 4 and 5, where the vehicle is fully autonomous and no driver intervention is required. Now, let's talk about the architecture behind the vehicles. Traditional cars use a distributed architecture with hundreds of isolation EQs. These creates complexity and bottlenecks. We are currently moving to domain-based architecture, grouping controls by function, but the future is centralized architecture, where the zone-based controls send massive amounts of data to central driving beam processing. How do these components talk to each other? Inside the vehicle, the traditional CAN bus is reliable but too slow, with only 1 megabit bandwidth. It's insufficient for video data. Therefore, the industry is shifting to automotive Ethernet, which offers gigabit speeds and better security. Externally, we have V2X vehicle to everything communication using either Wi-Fi based or 5G to see blind spots the sensor can't see. For a car to drive itself, it's not sense the world. We use RTK GPS for centimeter level positioning. We use cameras for reading signs and LiDAR for precise 3D mapping. But interestingly, the paper classifies high definition maps as a virtual sensors. As is shown in the 7-layer structure on the screen, these maps provide static data like lane geometry, which is fused with real-time sensor data. After sensing the processing, the car needs to move. Traditional mechanical linkages are being replaced by X-by-wire technology. This means steer by wire and brake by wire, enabling full digital control. Future platforms will likely use distributed drive within wheel motors, allowing independent torque control for superior maneuverability. This is the brain of the vehicle. How does it learn? There are two main approaches. First, data-driven methods, like deep learning. This is like end-to-end learning where the car learns from millions of miles of driving data. It handles complexity well, but it's hard to debug. Second, principle-based methods, which use explicit geometry rules and search algorithms. These are variable and safe but can be rigid. In conclusion, The research suggests that neither hardware nor software alone can solve the autonomous driving challenge. We need to bridge the gap by integrating centralized hardware platforms with the hybrid decision making algorithms. Thanks for listening.